Our next section is 11.6. It's called Solving Systems with Gaussian Elimination. So this is where matrices and systems of equations intersect. So what we're doing is, as I told you, this chapter was several methods for solving systems of equations. So what we're going to do is we're going to let's start with our first example. Let's go with the basic one, 2x plus 3y equals 6, and x minus y equals 1/2. Now clearly this one is really basic. You're probably going to solve this with elimination or substitution. Pause the video if you want to try to do that on your own. I came up with 3/2 1 as our solution. But I'm going to go ahead and use this simpler system and plug it into a matrix, and we're going to solve it using the Gaussian elimination. All right, so the way we stick it into our matrix is we take our coefficients of our variables and we stick them in using just the numbers. So the x coefficients go in the first column, the y coefficients go in the second column. If we had a z, that would be our third column. And then the right-hand side of the equation, we draw a line here, and we put the right-hand side like this. All right, so this is our system put into a matrix. So we're going to solve this. So the goal here is to get, so we're only looking at the left-hand side. The right-hand side is our solution set. So the left-hand side is what we're worried about. We're trying to get a diagonal of 1s, and everything else will be a 0. So it's called the identity matrix. So 1 and 1, 0 and 0, and then we'll have some number, I'll say A and B here. And the whole point is that this first row means that 1 times x, this is the coefficient 1 of x, plus 0y equals some number A. And the second row means 0 x's and 1 y would equal b. All right, so the way we do this is we can add together rows. We can multiply by constants, positives or negatives, or fractions. And that will help us to try to get these zeros here and then eventually 1s. All right, so let's just start with our example here. I have found that you start in the bottom left corner first. So if I want to make this 1 right here a 0. I noticed that if I took row 1, now I always use notation like I did with my systems. If I take row 1 and add -2 times row 2 and then replace my row 1. Sorry, replacing row 2, not row 1. Replace my row 2. So watch what I'm going to do. So I'm going to I'm not making any changes at all to row 1. I'm going to say it's 2, 3, 6. It stays as is. So, but for this one, I'm going to replace my row 2. This is what I'm operating on. So I say row 1, which is 2, plus -2 times 1. That gives me 0. Well, I have to do the same thing here. I've got 3 plus -2 times -1. So -2 times -1 makes +2. So 3 plus 2 make 5. Then we take 6 plus -2 times 1/2. -2 times 1/2 is -1. So 6 plus -1 makes 5. So I'm one step closer to getting this identity matrix. I got a 0 here. I tell people wait for the 1s till the very end. Those are easy to get. Work on the 0s first. So we got this bottom left 0. Now we need to get this 0 here. So the way I'm going to get that 0 there is I'm going to take row, use the same colors. If I take row 2, multiply -3 times row 2, and add it to 5 times row 1, that's going to give me a 0. So that'll be my new row 1. All right. So taking 3 times row 2, so 3 times negative 3 times 0 is 0, plus 5 times 2, make 10. That's my top left. Okay, this guy here, so I'm going to do this one next, the 3. So negative 3 times the 5 makes negative 15, plus 5 times 3 makes 0. Okay, negative 3 times 5, negative 15, plus 5 times 6, so negative 15 plus 30, make 15. Now I'm not changing row 2 at all. Notice that this is the only one I'm changing. So I have a 0 here and a 0 here. Once you get zeros in all your spots that you need, in this case it's only the left-hand side is only a 2 by 2. So I only had to get this one a 0 and this one a 0. So then I can take the first row, and I need this guy here to be a 1. So I'm going to multiply by 1/10. So I'm going to say row 1 multiplied by 1/10. It's the same thing as dividing by 10. Becomes my new row 1. So if I do that, 1/10 times 10 is 1. 1/10 times 0 is 0. 1/10 times 15. Whoops. 1/10 times that 15 gives me 3/2. All right, I didn't do anything to row 2 yet. I will. Once you get good at them, you can do a couple steps in one. So now I need this guy here, this 5, to be a 1. So if I multiply by 1/5, so I'm going to take 1/5 times row 2 and replace row 2 with that. Oops, that's supposed to be a 2. So row 1 stays the same, 1, 0, 3/2. Row 2, 0 times 1/5 is 0. 1/5 times 1/5 is 1. 5 times 1/5 is 1. So this means that x equals 3/2 and y equals 1, which is what I told you up here in the beginning if we were to solve this. All right, let's try another one that is, how about let's do a 3 equation, 3 variabled system. All right, so remember, you can always work the other method, but I want to show you the matrix version. Keep in mind, this is the way computer programming would work this. It's matrix style. So it works the very same. We're going to put our coefficients in. 2, 3, -1, -2, 3, -2, -9, and 9. All right, clearly this is going to be a little more complicated than the last one. All right, so I told you in the last one that you aim for the bottom left-hand corner. So notice that the identity would be 1, 1, 1, and zeros everywhere else. So when I was teaching this a couple years back, I looked up methods for solving these so that you don't undo things. It's easy to undo steps. So, and the suggestion was you start here, go this direction, and then go this direction as you're solving for zeros. So I'll show you what I mean. What I mean is I'm going to start with this one. I want to make this guy a 0 right here. So to make him a 0, I have some options here. I'm going to take -2 times my row 1 and add it to my row 2 to replace my row 2. So those are my steps. I always write my steps, so I always know what I'm doing. 1, I'm not changing. 3, I'm not changing. I'm going to go ahead and write them down so I don't make any mistakes with those. So row 2 is the one I'm changing. So I'm taking -2 and multiplying it by row 1. So I've got -2 times 1 gives me -2 plus 2 gives me 0. Then my next entry, I have -2 times -1 makes +2 plus 3 makes 5. My next entry is -2 times 1 is -2 plus -1 makes -3. Then negative 2 times 8 gives me negative 16, plus negative 2 gives me negative 18. All right, one step down. So my next one, I said to go in this order. So we're going to work on this 3 here. We want him to be a 0. So I'm going to say, let's multiply negative 3 times row 1, add it to row 3, and replace my row 3. All right, I'm not changing row 1. I'm not changing row 2. I am changing row 3. So negative 3 times 1 gives me negative 3, plus 3 gives me 0. Negative 3 times negative 1 gives me positive 3, plus negative 2 gives me 1. Negative 3 times 1 gives me negative 3, plus negative 9 gives me negative 12. Negative 3 times 8 gives me negative 24, plus 9 gives me, what is that, 15? Negative 15? Okay, just double checking there. All right, another one down. Next one is to make this guy here a 0. To make him a 0, so here's the key. You don't want to undo this one or this one. So you might say, hey, just take row 1. Oops, that's pencil, not marker. You might say take row 1 and add it to row 3 and make a new row 3, right? Because they're additive inverses. But the problem is, do you notice what would happen to this entry right here? Row 1 plus row 3 makes a 1. So I would be undoing the 0 I just created. So for that reason, this step will not work. If you ever find that you make a step that undoes something, just go back and change it, is my suggestion. So it looks like we're going to have to use row 2 to get rid of this guy here. So if that's the case, we're going to take row 2 plus negative 5 times row 3 and replace my row 3. All right, so doing that, I'm keeping row 1 as is. I'm keeping row 2 as is. Remember, I'm only replacing row 3. All right, so my next one here, I've got row 2, so 0 plus negative 5 times row 3, which was 0. So that's 0 and 0 make 0. That's why we chose this one. Then we have row 2 is 5 plus negative 5 times 1. That's negative 5. 5 and negative 5 make 0. That's the whole point. Then my next one is row 2 is negative 3 and negative 5 times negative 12. So that negative 5 times negative 12 is positive 60, and negative 3 make negative, oops, sorry, not negative, positive 57. Okay, then we've got row 2 is negative 18, and then negative 5 times 15. So negative 5 times negative 15 make positive 75, and then plus negative 18 make 57. Oh, that's convenient. These are both 57s. All right, so I often suggest you worry about the ones, because I need a 1 here, 1 here, 1 here, and a 1 here in the diagonal till the very end. But sometimes you may recognize that it's going to be much nicer for you to get rid of a giant number like 57 now. So if I take 1/57, that's the same as dividing by 57, times my row 3 and replace my row 3, it's going to make that row 3 much smaller and nicer to work with. I don't want to multiply 57 by anything. Okay, so I'm just going to replace my row 2. I'm sorry, I'm going to rewrite my row 1 and row 2. And row 3 I'm going to multiply by 1/57 or divide by 57. So that gives me 0, 0, 1, and 1. That's nice. So I will tell you that there is one method that stops here. And the reason why, I'll show you. If I were to convert this guy here back into equation form, that would be 1x minus 1y plus z equals 8. That's my first one. My second one would be 0x plus 5y minus 3z equals negative 18. That's my second one. My third one is 0x plus 0y plus 1z equals 1. Can you guess why someone might stop here? Hopefully, you can see that we can use back substitution. If z is 1, can't I take z and plug it in to this equation up here and say 5y minus 3 times 1 equals negative 18? Which means that 5y equals, if I add 3, negative 15, which makes y negative 3. And then I have y and z. I can plug them both into the first equation. X minus y is negative 3. Z is 1, 8. So this gives me x plus 4 equals 8, and x equals 4. So the solution here gives me 4, negative 3, 1. All right, so I'm going to keep working this same matrix. I just rewrote it from up above, from up there. If I were to completely solve this guy matrix style. So I got all of these in zeros. So the next one is to start this way and go this way. So I'm going to start with that negative 3 there. To make that guy a 0, again, pay attention to what you're doing. Make sure you don't undo anything, because notice I have a 0 there. I don't want to undo him. So I think I'm going to have to use row 3 with my row 2. So if I multiply 3 times row 3 and add that to row 2 and replace my row 2, that should work. So I'm going to rewrite the row 1. I'm going to rewrite row 3 because I'm not changing that guy at all. So row 2 is changing. So 3 times 0 plus 0 is 0. 3 times 0 plus 5 is 5. 3 times 1 plus negative 3 is 0. 3 times 1 is 3. 3 plus negative 18 is negative 15. All right, again, I can divide, if you notice that row 2 there divides through by 5. The only reason I would do this is if it produced whole numbers. If it's going to make fractions, I don't want fraction to work with fractions along the way. I'm probably going to wait till the end if it produced a fraction. So I'm going to replace my row 2 by dividing by 5. Okay. Notice we have 2 of our solutions. We have 1 and we have negative 3, which we know from above, the back substitution method is true. All right, let's just finish this guy though, say we did. All right, so this guy here, I need to get rid of this. He needs to be a 0. So to make him a 0, again, make sure you don't undo anything, but I'm going to use row 3. I'm going to take row negative 1 times row 3 and add that to my row 1 and replace my row 1. Okay, that gives me, so I'm going to go ahead and rewrite my row 3, and I'm going to rewrite my row 2. All right, so my row 1, we've got negative 1 times 0 plus 1 is 1. Negative 1 times 0 plus negative 1 is negative 1. Negative 1 times 1 is negative 1 plus 1 is 0. Negative 1 times 1 is negative 1 plus 8 makes 7. All right, we're almost there. The last thing I need to do is to get rid of this guy here. So to get rid of him, I'm going to use row 2, add him to row 1, and replace my row 1. All right, row rewrite row 3, rewrite row 2. Now rewriting row 1. So 0 plus 1 makes 1. 1 plus negative 1 makes 0. 0 and 0 make 0. Negative 3 and 7 make 4. So now I have the identity matrix, meaning that I have all 1s and everything else is 0. And according to this system, right, if I were to rewrite this equation format, x is 4, y is negative 3, and z is 1, which we know is true because that's what we found when we did back substitution. So it may be more difficult than the substitution elimination method, but again, it's very useful in computer programming, a quick way of solving